Okay, so let's start with the next session. Our next speaker is Thomas Hertog, who's going to talk about quantum cosmology, predictions versus observation.
Where is it? Oh. Okay, well, thanks for the organizers for giving me the opportunity to speak here. It's a very nice meeting so far. The subject of my talk is quantum cosmology, and you should view this as being complementary to Liam's and Cliff's talks this morning. It deals with, as far as the cosmological applications are concerned, it deals with another part of the prior that is needed in cosmology to make predictions. My talk will be focused mostly not on the formal development of quantum cosmology, which is a subject on its own, but on its relation with observations. What really do we get out of quantum cosmology? A milestone paper that really led to a lot of development in quantum cosmology is this old paper by Hartle and Hawking, where they first formulated the notion of a wave function of the universe, the central object in quantum cosmology from which all predictions are ultimately derived. But it's fair to say this is a very abstract paper, and Slava once told me the paper only got interesting all the way towards the end when it stopped. And in a way, it's true, it remained unclear for many years how really is a wave function of the universe, how that relates to our actual observations, and that will be the main subject of my talk. But this wasn't the birth of quantum cosmology. Quantum cosmology goes back way earlier. Here's a paper in Nature by Georges Lemaitre. He's the one on the right there on the figure, on quantum cosmology. But as he rightly points out in the middle of his paper, he writes somewhere, well, it may be difficult to follow up on this idea. And well, he was quite right. We still really don't have a fully fledged, precise framework of quantum cosmology. The first question I would like to address in a very simple way is, why should we be interested in quantum cosmology? Obviously, it's a route towards observational signature of quantum gravity, just as exploring the structure of the string landscape is a route, and so forth. But there's a more precise, there's a more fundamental feature to it, which I would like to highlight, and that has to do with the prior that goes into inflationary cosmology, without which you really don't have any firm predictive framework. And I would like to illustrate this in a very simple way with a very simple model of inflation consisting of one scalar field with an asymmetric potential. Clearly, we have inflationary solutions rolling down from one side. We know very well what the predictions are of those solutions, what the perturbations will look like, the spectra will look like, and so forth. But models of fundamental physics have different kinds of inflationary solutions. In this case, the universe may equally well have rolled down from the other side, yielding a slightly different CMB. And then what? What do we predict? That's the framework, I think, in the very simplest terms, where quantum cosmology comes in. At the classical level, these solutions you can study, and those solutions you can study, but there's no connection between these two sets of inflationary solutions. And indeed, at the purely classical level, you don't even know, you can't even answer the question why inflation started in the first place, or how many E-fools would be preferred there. There are all kinds of questions that remain unanswered. So you need a quantum cosmology. What's the goal of it? It's just a bigger theoretical framework in which those kind of questions are well posed and can be answered. The reason is simple. A wave function of the universe does not describe one set or one classical universe. A wave function of the universe is a function of the configuration of matter fields on a space-like surface, and it therefore describes an ensemble of universes. That's the key conceptual step in going from classical to cosmology to quantum cosmology. Once you have an object that unifies the ensemble, that unifies different inflationary solutions, you're in business. Because as usual in quantum mechanics, a wave function of the universe implies relative probabilities between different universes or observables and so forth. And then you have a framework to make robust predictions. That's the conceptual framework. That's the appeal of quantum cosmology. Of course, the key question then becomes, well, what is this wave function? How do we even talk about a wave function? What's its precise form? So the outline of my talk will be in a very in the setting of the Hertog-Hawking paper in '83, where they made a concrete proposal for a kind of ground state wave function for the universe. What are, in that framework, the predictions for inflation? I'll discuss how entropic selection emerges automatically in the framework of quantum cosmology. And then towards the end of my talk, I say a few words on how to go beyond the Hertog-Hawking framework, which is purely semi-classical in the sense of it's a WKB proposal for a wave function of the universe. It's not a complete theory, and it's a very active domain of research to go beyond that. So this is the outline of the remainder of my talk. So first of all, very few words on the basic framework of quantum cosmology. So the proposal of Hertog and Hawking comes down, roughly speaking, to a kind of regularity condition, to a kind of replacement of the singular Big Bang in classical cosmology by a regular, what they call a saddle point geometry, or sometimes it's called an instanton. It's a kind of boundary condition at the origin of the universe which they impose, and which is behind their proposal. And what exactly are they saying? They say, well, we associate to all classical universes, we're going to associate to those universes a saddle point, which is complex, which deviates from the classical evolution near the Big Bang, and we're going to weight those different saddle points by their Euclidean action. That's the essence of their proposal. E to the minus the Euclidean action of the saddle point provides the same classical approximation to the wave function. The wave function is the function of various of the configurations on the final boundary on the surface where you evaluate the wave function. Now, precisely because those saddle points are generally complex solutions of the Einstein equations, which behave like real Lorentzian classical solutions when the scale factor becomes large, but they're much more complicated down here. Because of that, their Euclidean action is complex as well. In other words, their wave function has a non-trivial amplitude and it has a phase factor. Well, a wave function of that form, as you know very well, will predict classical Lorentzian evolution of the universe whenever, in whatever regime, that phase factor oscillates rapidly compared to its amplitude. In that way, they recover classical cosmological evolution, and it turns out that this is the case when the scale factor is sufficiently large. The cosmologies that are predicted by the wave function are those which are given by the integral curves of the phase factor. And this is the crucial point. Each cosmology, each history of the universe, so to speak, comes with a certain amplitude, this A, which is conserved along cosmological evolution. That's the key point. Associated with each cosmology, you have a certain amplitude. So they end up with a kind of multiverse, a kind of ensemble of cosmological solutions weighted by the no-boundary saddle points. And perhaps the most significant and universal prediction of this particular wave function, this particular proposal for quantum cosmology, is that those classical cosmologies that are predicted by the wave function all have an inflationary phase at early times. This, to my mind, is the most appealing feature so far of the no-boundary wave function. And it stays nothing else than inflation is probable, given this quantum state. It's a very significant fact. We always think, well, inflation requires fine-tuned initial conditions. It's very unlikely. If the universe is in this quantum state, no. Inflation, classical cosmology emerges through inflation. And it has, in a landscape context, an important implication. It means that in a very big landscape, you will only, if the universe is in the no-boundary quantum state, you will only populate those vacua which can be reached through slow roll, which are surrounded by one or more patches of slow roll, where the slow roll conditions hold. So here, this is just illustrated in a simple phi squared model. All the histories, so these are 5 different background cosmologies that you get out of the no-boundary wave function, and they all, if you evolve them back in time, so that's the instantaneous Hubble rate, they all lie on this narrow line characteristic of inflationary solutions. As I mentioned, all these histories come with a certain relative probability. The no-boundary weighting on backgrounds has the characteristic 1 over V factor, where the value of V that enters is, roughly speaking, the potential evaluated at the origin of the saddle point. That's, roughly speaking, connected to the number of E-folds of the corresponding classical inflationary solution. And then, of course, the wave function is a function of all data on a space-like surface. So if you include perturbations on that surface, you're going to have weighting of various perturbations, and that weighting is really just the standard Gaussian wave function of the perturbations in inflation, and that is because the irregularity condition, that is the defining feature of the no-boundary wave function, not only selects for inflation, but also puts the perturbations essentially in their Bunch-Davies state when the universe is very small. So this is then the ensemble of histories, the ensemble of universes, the multiverse you get out of the wave function of the universe, together with their relative probabilities. And from those probabilities, you can derive predictions for local observations. So that's in a nutshell the framework for quantum cosmology. And I'll now move on to 2 very simple applications, really, to illustrate how this can be useful for cosmology. So the first application is just, well, we can look at that probability distribution given by quantum cosmology and see what it predicts, or see what are the generic predictions that come out of this. Of course, the predictions are going to be tied to the structure of the potential that you assume. There's no such thing as the wave function of the universe predicting anything independent of the structure of the potential. So in that sense, as I mentioned, my talk is complementary to what Liam and Cliff were discussing this morning. It's really the combination of a wave function of the universe and the structure of the landscape which provides you with concrete predictions. In order to illustrate the effect of the quantum state, I'm going to assume for now like an unbiased, simple landscape potential. And by unbiased, I mean that the various inflationary patches that occur in the landscape occur with roughly equal frequencies somewhere. And I'm going to restrict, just for illustrative purposes, to single field inflationary patches. And I'm going to assume that semi-classical no-boundary wave function that I discussed. Exactly analogous to the quadratic potential I just discussed, the no-boundary wave function will A, select the inflationary patches of this landscape, and B, it will, with each inflationary patch of the landscape, it'll predict a one-parameter set of inflationary backgrounds labeled by the number of e-folds or whatever parameter you prefer. And so in the end, you get a relative weighting of those inflationary landscape regions. You add up the probabilities of the histories associated with different landscape regions, and you get a relative weighting. And then you have to ask an observational question. Because, of course, we don't observe, we're not somewhere outside that entire ensemble of universes, and we don't observe this grand structure. No, we're somewhere inside the universe, in one of those histories, rolling down from one of those patches, and we want to figure out in which kind of universe we are. So the predictions for observations are given or governed by conditional probabilities. They're really correlations. They're correlations between an observable feature of the universe we're interested in and our existing observational situation. So one way to express such correlations is just to compute a conditional probability for some observable, say the CLs, given our observational situation, some coarse-grained description of a set of data. Our observational situation can be described by a set of data. And all we require is, of course, that it exists in the history that we're in. So then you express this quantum mechanical probability in this landscape. So what is going on here? There's a sum over the various different inflating patches of the landscape. There's an integral over all the histories associated with a given inflationary patch of the landscape. And then I'm just using basis rule to write this out. This is the probability of the standard observable that you would calculate in classical inflationary cosmology if you do perturbation theory. That's the probability, say, hey, if you think of O as the CLs, what are the CLs given a certain inflationary patch? That probability will be high if the CLs are those standard predictions and very low if you're just off. Then that probability in this case, and that's the input of quantum cosmology, is multiplied by a certain non-trivial prior. And that prior really consists of two factors, roughly speaking. This thing is what's often called an entropic selection factor. We're just taking into account our observation situation. And then that selection factor is multiplied by the no boundary weighting we discussed. So if you're interested in the relative probability of two different kinds of CLs, then the CLs are given here, then those relative probabilities will be given by the ratio of this factor multiplying each of those CLs. So that's the new input that quantum cosmology provides.
How do you calculate those intervals if you've got an eternally inflating?
I'll come to that. Yeah, so now I come to how you evaluate that integral. I'm going to describe it qualitatively. So this is the no boundary weighting, okay? And then it's multiplied by this selection factor. Now, quite clearly, this selection factor is going to be very small for universes which are small, and it's going to go to 1 when the universe gets sufficiently large so that we're certain that our observational situation, which has some probability to be occurring in any Hubble volume, when that observational situation occurs almost with certainty. And so what this selection factor is doing on the no boundary weighting is the following. So I'll illustrate it with two different patches, power law patches, where you have a lower bound on the histories in the no boundary ensemble. You have the threshold for eternal inflation, just as you were asking, and then way above that, you have the Planck density. At the threshold of eternal inflation is an important threshold because it's at that point that the perturbations have a big impact on the global structure of the universe, and in particular, they make the universe very large. So at that point, the selection factor rapidly goes to 1. But if you go higher than that, the no boundary weighting, which is multiplying the selection factor, sharply disfavors starting even higher. And so what you get is a peak in the probability distribution around the threshold of eternal inflation, and further then the distribution decays. Similarly, in plateau-like patches where the regime of eternal inflation occurs near the top of the plateau, again, you find a strong peak around the threshold for eternal inflation and essentially no probability of the weighting lower down. The key point is the value of those peaks then. So the bottom line is that the integral is dominated in each patch by the universe emanating from around the threshold of eternal inflation, but the relative weighting between these different patches is governed by the value of the probability distribution at the peak. That value is given by the no boundary weighting, and it is essentially set by the value of the potential at the threshold for eternal inflation. And this is the origin of the argument that the no boundary weighting favors those inflationary patches of the landscape potential where the eternal inflation threshold lies at a low value of the potential, which are precisely those plateau-like directions. So roughly speaking, if you then go to the Planck data, well, in the context of quantum cosmology, it's very different, as Ben already mentioned as well. It's a very different way of looking at those Planck data, of course. In the context of quantum cosmology, you have definite predictions. Given a quantum state, well, you're gonna predict, in this case, this region near the bottom, because that's where these plateau potentials with a low eternal inflation threshold lie. The predictions, of course, I mean, this is not the most useful diagram to really spell out the details. You would have to specify the structure of the landscape for a start to go beyond this. But I think there are two takeaway messages here. All these models are part of the same theory, and the quantum state provides you with a very sharp prior in that space of what we would call inflationary patches. The prior is very theory dependent. That's really the essence of the debate earlier this year. If I had chosen a different prior, I would have ended up somewhere completely different in this diagram. If I had assumed a specific structure of the landscape, I would think that I would also end up somewhere else, or you would be able to refine those predictions for sure. As I said, I'm assuming an unbiased landscape for the purpose of this talk. Okay, but this was a very simple example in which I did not allow for a variation of the amplitude, Q of the fluctuations, or of the cosmological constant, and so forth. So now you can consider larger landscapes, and the game becomes much more difficult, of course, because you have many more variables to play with. And in particular, so I'd like to touch briefly on this. This entropic weighting factor did not do very much in the previous analysis I presented. It just lifted you to the threshold of eternal inflation in the various inflationary patches, and that was it. But in a larger landscape where Q varies and lambda varies and I don't know what varies, of course that entropic selection factor, as was worked out in detail by Tegmark and his collaborators, that entropic selection factor becomes also cosmology dependent. It's essentially the fraction of matter that ends up in galaxies times the number of Hubble volume. But of course, the fraction of matter that ends up in galaxies in these different universes is Q dependent and lambda dependent and so forth. So it plays a role in combination in those landscapes with the no boundary weighting. And in particular, talking about lambda and Q, it's this fraction of what enters in the final probability distributions is the fraction of matter that ends up in galaxies, which is a function of lambda, Q, and the time of observation, times that same no boundary weighting. And you might remember there's these famous lambda Q plots, which were highlighting really the entropic selection. It's a way of representing Weinberg's argument for an entropic prediction of lambda. And it was pointed out by many people really that Weinberg's predictions, when Q varies as well in the landscape, become a lot worse by several orders of magnitude. It's this blue dot, because essentially this region for lambda grows when you allow Q to become larger. You can still form galaxies. This white region is selected by the selection for the entropic factor, but the argument that was used to argue that Weinberg's predictions become so much worse, again assumed a flat prior on this space. It assumed, in a way, ignorance about the underlying quantum state. It's a very simple exercise to redo this calculation, but with a no boundary prior, and you get a different result. Again, highlighting that there can be no debate about naturalness, fine-tuning, likelihood, without specifying the theory, without specifying the quantum state. And in this particular example, it works out nicely. The no boundary prior puts you back where Weinberg's original predictions were which peak around a much smaller value of lambda compared to when you were assuming a flat prior. So in the last, come now to the last part of my talk. It's a bit more towards high energy physics, towards string theory. So there are key open questions here. I presented an approximate framework, which I think is conceptually appealing, and furthermore, it makes definite predictions. But there are two serious unknowns, which is A, what is the structure of the landscape? This is equal input than the quantum state. And B is, okay, should we really think in fundamental physics about a wave function of the universe? What's its precise formulation? Is it unique? It's a very important question. Or is it a hopeless game that we should allow, that we should scan some kind of space of quantum states or whatever? And so I'd like to end by sort of briefly sketching a recent program that aims at getting a better handle on the quantum state. And that's holographic cosmology. It's a program pursued for a number of years now by many people, aimed at essentially applying the lessons of ADS-CFT to a cosmological setting. As I mentioned, the wave function of the universe is evaluated as a function of the configuration on a space-like slice of the universe. That's a natural boundary, and therefore, at least one can hope there is a kind of holographic formulation. And in fact, a hint is the following. A hint that this might work is the following. So I talked about these saddle points. The traditional representation of the no-boundary saddle points is really a classical Lorentzian inflationary history glued onto a regular Euclidean de Sitter half sphere. That's really the classic representation. But really, this is a complex solution of the Einstein equations. There are many representations, which the only requirement here is regularity at the South Pole and real boundary data at late times. And the same saddle point has a representation in terms of a different complex geometry, where I just plot the absolute value of the scale factor here, in which a regular Euclidean anti-de Sitter space is glued at much larger values of the scale factor onto the same Lorentzian de Sitter universe. Now, how can it be that anti-de Sitter and de Sitter occur in the same theory? Well, it's very simple. These are complex solutions. The signature of the metric of those solutions is not defined in the interior. It's only defined at late times. It changes in the interior here. Here it changes from Lorentzian to Euclidean. Here it changes from Lorentzian to Euclidean in a different signature. So you have various representations of the same saddle point with the same action and the same boundary data. And in particular, this representation, which we stumbled upon really, is interesting. It turns out that the amplitude of that history here is given by what in ADS-CFT context is called the regularized Euclidean action of the, that's essentially a Euclidean ADS domain wall here, on the right-hand side. So that provides a natural route to connect the framework to high-energy physics or string theory by applying the Euclidean version of ADS-CFT. The Euclidean version of ADS-CFT is essentially a statement about the wave function of the universe. It associates to a Euclidean ADS space, which is a ball essentially, a boundary partition function, a partition function of a boundary field theory, and that field theory is deformed. That partition function is deformed. It has sources, and those sources are exactly the boundary data, the argument of the wave function, of the original wave function. So there's a kind of natural interpretation of Euclidean ADS-CFT as providing a statement about the wave function of the universe. And so that's a program which is pursued from various angles. Other angles which started from Euclidean ADS-CFT and did a kind of continuation to arrive at some DS-CFT setting, at the end of the day, come down to a very similar picture here. So far what's been done in this is, well, we've translated the semi-classical old quantum cosmology results into a holographic language. As also Paul McFadden discussed, we can write, we can calculate correlations of perturbations and so forth from a dual partition function. We can use the relative weighting provided by these different sources to calculate the weighting in the no-boundary wave function and so forth. What has not been done is to embed this framework in a complete, to have a concrete, fully consistent field theory realization of this setup. Essentially, the whole picture for now works with specific truncations of the Bullock theory, so it's restricted to certain operators in the field theory and so forth. What is appealing, however, is that this setup strongly hints that the wave function of the universe is, in fact, unique. Euclidean ADS-CFT, despite 15 years of work, always ends the no-boundary condition. It always makes use of a regular Euclidean ADS saddle points, and those regularity is encoded in the field theories that you have on the other side. So that's a hint that there may be universality in a way, uniqueness, or universality of its predictions, uniqueness of the wave function of the universe in the full theory. Okay, so it's time to conclude. Here are the main points. The wave function of the universe implies a prior over models, backgrounds, and observables in inflation. The specific case of the no-boundary wave function favors inflation rolling down from plateau-like potentials. It therefore naturally leads to the prediction of a low tensor-to-scalar ratio. Entropic selection emerges within the general framework of prediction in quantum cosmology. It's not about adding another principle to the theory or adding another input. The no-boundary prior restores Weinberg's successful entropic prediction of lambda, even in landscapes where Q varies. And there's a lot more work to do on taking this program forward, both on exploring the structure of the landscape potential and on getting a better handle on how exactly we should write down a wave function of the universe in quantum gravity. Thank you.
Thank you very much. We have time for 2 or 3 quick questions.
The no boundary wave function in the plane where q and lambda varied seemed to push you towards these catastrophic boundaries, or these boundaries where things didn't happen. And also in the case of eternal inflation, you were pushed to kind of boundaries. Do you think that might be a general statement? If more variables were allowed to change, that you would always be pushed towards these kind of boundaries?
Yeah, of course, even with a flat prior, you were pushed to another boundary. But yes, I think generally the weighting is strong and therefore will push you to the boundary. It's either flat or very strong. The weighting in the no-boundary wave function, for instance, was flat on lambda and very strong in Q. So it pushed you to low Q, and then it was just acting like a flat prior on lambda. So I think indeed with more variables, this may be the case.
So what worries me to some extent is this property that the wave functional is not normalizable. And am I right in stating that if I take this procedure and take, for example, absolutely flat prior, not the approximately flat as you do, that I will get the dominant contribution coming from potentials that is almost absolutely flat with epsilon very, very close to 0.
The contributions of the different landscape patches are set by the potential value at the threshold for eternal inflation. So there indeed, epsilon can be very small at that level, but that's way beyond the directly accessible observational regime. What exactly are those thresholds, or what's the distribution of those thresholds, is then again a question which one can analyze in a specific sector of the landscape where one has those potentials.
In other words, what I'm trying to say is, in some sense, you took epsilon as a prior, and then you got some prediction on R. Is that correct? And if you didn't take epsilon as a prior, you would tend to get epsilon close to 0, namely ns close to 1.
No, because there's a difference. It's true that you could think of it as epsilon being very small, but it's very small, way beyond our observational regime. So there has to be a connection between that regime of the potential and the accessible observational regime, where epsilon will be different. And that connection I have assumed to be simple in my examples. Perhaps it's going to be more complicated in specific sectors of the landscape. But it's not a direct connection between the no-boundary prior and the epsilon we observe.
Okay, so we should move on. So let's thank Thomas again.